I'll be talking about hxtorch.snn, machine learning inspired spiral neural network modeling on brain scales 2. And before I get started, I want to say that I'd like to split this talk in like 3 parts. The first part is motivating what we want to do. Second part is how we do it. And in the last part, I want to just tell you what we can do with it. So to start off, I wanted to set kind of like the mood for the talk and tell you what I think about machine learning and neuromorphic hardware and how we maybe can connect the two. And so if we think about machine learning in the classical way, we think about matrix multiplications and backpropagation with these arrows. And neuromorphic hardware, on the other hand, shows us that there can be fast inference and local learning, and we represent, in the spiking case, spiking neural networks by individual entities on the hardware, in our case. Maybe also different on other hardware, but this is what I want to focus on. And so, to put this a bit more into context, on the machine learning side, we have always some form of tensor data and do numerical calculations with them. And our modeling focus is on the arithmetics, on the algorithms. We have typically auto differentiation, which we use, and the training methodology. And those are all parts that we want to use for when we like to train spiking neural networks on neuromorphic hardware. And on the neuromorphic hardware side, we have event-based sparse data instead of tensor data. And we actually emulate potentially spiking neural networks. And the modeling focus is not so much on the arithmetics, because that we ingrain in our hardware, but more on how can we describe the networks, how are the biological analogies. So what's the neuron, what's the synapse, does it have the same properties as our biological neuron, or different one. And also we typically talk about morphology of the neurons and the topology of the network as a whole, more so than on the machine learning side. And because we want to have the same representation as in biology, we also have to convert the observables unit-wise or otherwise, because the neuromorphic hardware obviously has different units, maybe digital bitwise units or time units which are different than the biological counterpart. And so the question that we are trying to solve is the combination beneficial? How can we combine this to make it work the best way possible? And so to introduce the hardware that we are going to try to build into the machine learning framework, this is brain scales 2. It's developed in Heidelberg. It has analog adaptive exponential neurons, and you can choose between current-based and conductance-based synapses. And the network dynamics are 1,000 times faster than in biology due to the fact that our capacitors are just smaller than the biological ones, more or less. If you want, you can look up more properties on the respective papers, hardware and software-wise. And I also would like to go a bit more into details on each chip that we have. There are 512 neurons with 256 synapses each, with a configurable weight. And aside of that, we have 2 embedded plasticity processors with SIMD units, which can alter weights or other parts of the network topology or configuration. And because it will be used later on, there's also parallel ADCs for reading out something like membranes or correlation measurements on individual synapses. And the software is layered, and we have multiple front ends, one of which I will show you here. This is the PyTorch version, and the other one is the PyNN version. Okay. And on the right-hand side, you see how this is embedded into an actual experimental setup where we have the chip on the top with the different components, and an FPGA for communication in more real time than the host computer can do, and the host computer where we set up our experiment and interact with it. And to go a bit more into detail about what is special about this hardware and how it interacts with machine learning frameworks, I want to talk about time-continuous physical emulation, which this system does. So we can't stop the network dynamics, we can't resume them, we can't store the state variables completely, we can't restore them. And due to this fact, we have to have the complete network in a physical representation during execution, which is especially true for our current networks. When we have feed-forward networks, we can obviously like execute one layer, then store the results, put them into the next layer, and so on. And this also means that prior to execution, we need the complete network, which I will hint on later when we see the interface in the machine learning framework. And this also means that the physical size of the hardware limits the recurrent network size, and we can mitigate this in part by either temporal or physical partitioning, which you can see here on the right-hand side, where when we have feed-forward connections, we can temporarily partition just by executing one thing after the other. And when we have recurrent connections, such as in the output layer here, we have to physically partition them onto multiple chips which run concurrently and interface them somehow in network emulation real time. And so when we want to integrate this now into a machine learning framework, and for this we chose PyTorch in our case, we already heard why this might not be the best idea, but we still want to do it to reap all the benefits from the machine learning community, training-wise and data representation-wise. And so if we look at this simple example of a two-layer feed-forward network, which we can see also here on the left-hand side in vanilla PyTorch code for rate-based with linear layers and rectified linear units as nonlinearity. And this is how it looks like. And the question now is, how can we implement this on our hardware, or how does it look like if we want to run like the same network but spiking on our hardware? And so the first thing that comes into mind is, okay, obviously the layers somehow need to have different names because we don't have rectified linear units, but for example, LIF or leak integrators. So this still looks like really the same, but then we have the problem of this time continuity. And as I said, we have to know the complete network prior to execution, but this is not possible with PyTorch typically, because when you run this line, it just executes this line, and you want to have the output of this first synaptic layer here. And how we solve this is by, okay, this one I forgot. This is the same representation in a bit more graphical format, where in green in the middle you have like the tensor data. Each layer is represented by one column here. Yes, and the data flow in between them. So if you want to solve this time continuity, what you have to do is, or one idea to solve this is to carry something like an experiment on the hardware through each layer, and explicitly after construction of the network execute this. And only after construction fill all the data in here. And this is what also is represented on the right-hand side, where you like in parallel to the PyTorch graph generation, you generate your network on the hardware, execute this, and then afterwards fill in all the data that you have acquired. And what this allows us to do then is to reap all the benefits from the machine learning framework. And one of these is automatic differentiation, which we want to have for training the networks. And this is pretty easy to do then, because what we only have to do is like add the backward pass somehow. And there are two ways to do this. One is explicitly writing down the backward pass for like the model neuron that you have on the hardware. And the other way is to write a simulation of the same neuron or of a neuron which is similar enough that it still trains. And the last version also allows you to only simulate with the same API, which is kind of nice because you can, for example, only put the last layer on hardware and train with this, and then you saw, okay, it works, and then put the next last layer on hardware and train with this and see, okay, it works. And for recurrent networks, we have the problem that you have to time unroll in the backward pass over the recurrent subgraph. And this we solve by just allowing to attach to the subgraph a complete backward pass. Okay. Now, a second point I want to talk about in detail is data conversion, because on the hardware we have sparse data, we have event-based spike communication, but PyTorch doesn't work this way, at least not easily. And so we somehow have to interpolate all our sparse data onto a dense grid. This is represented here on the right-hand side, which is information efficiency-wise obviously not a good idea, but then we can train with known methods. And the second point is that when we have this network PyTorch execution lines, we don't really get the real data, but we only get like a handle to the data which will be present after execution. And additionally, maybe for one layer, we have multiple observables like spikes or an membrane potential, and this we just return in a structured way, which in the end will have or store torch tensors with the correct backward pass attached to them. But not on construction. Okay, so now I've shown you the complete API, which is required to run machine learning-based experiments on Brainscales 2. And the question now is, what can we do with it? And in the poster session, I showed you the second application here, which was IMDD optical communication. This is a real-world application, but here I only show you like a toy example application, which is the same network as we used before. 2-layer, one hidden layer, one readout layer with leak integrators. And the data set which we are looking at is the yin-yang data set, which has 3 classes of elements. And we spike time code the classes. And this is what the output of one of such point here looks like, and how we get the answer of this output is just max over time. And we see that this actually works quite nicely. I think, if I remember correctly, above 80% it says that backpropagation works on this data set. Yes. And since we will have a tutorial session on Friday, this exact experiment you can also try out then as an interactive session on the eBrains platform. Okay, so to wrap things up, what have I shown you? So we can emulate spike neural network models on Brainscales 2, which are integrated into the PyTorch ecosystem. And due to the fact that the hardware operates time continuously, we have to separate this execution and description of the network. And we fully integrate the gradient estimation, which all of you know from machine learning. And you can inject this with a simulated numerical model. For example, like Norse, which we also, I think, used in the IMDD example heavily for this. And it especially enables us to use the same training methodologies that are already present for all the other problems machine learning wise. And as application, hopefully there are plenty more to come, but I have shown you the yin-yang dataset classification with a simple feed-forward model with surrogate gradients. And the 2 other ones are also the IMDD optical communication and the yin-yang dataset with NPOP, which is currently work in progress. And so what is to come in the future? There are 3 points I want to point out. The first point is larger networks, because currently we are limited to this one chip, which is obviously not so large, but it is more of a backend problem, because as you have shown in the API, you don't see anything about how this is partitioned on the chip. So this should just work if we get the backend right and have the inter-chip communication present. And the second thing is that the information is coded in PyTorch very inefficiently, as you have shown, because we have to densify all the data. And for this, we are currently evaluating different machine learning frameworks which operate on event-based sparse data. And one example for this is Structs. And I have pointed out in the beginning that there are these on-chip plasticity processors, but we don't use them yet. Mainly because we don't really know how to include or incorporate online or local learning into the machine learning framework, because it's kind of like orthogonal to learning without backpropagation. And this is another point that we want to try to solve, to integrate the online or local learning parts into the same interface. So with that, I'm at the end of my talk, and want to remind you that you can try out yourself the application that I've shown you, and play around with the hopefully machine learning friendly API. Yes. Thank you for your attention.